This solar heater will be described by this video, and this is my third step to heaters which can produce heat with temperatures up to 100 degrees Celsius and with a cost less than 1 cent per kilowatt hour, and it is about 5 times cheaper than the cost of heat from natural gas and 10 or 20 times cheaper than electricity. This mild heater was the first step, and it can heat water up to 70 degrees Celsius, and I remind you that it consists of a wooden frame, a layer of thermal insulation and a black polymer sleeve for water which is heated by solar energy. It is obvious that the main cause of our cheap heat is the low cost of our solar heaters, which are several dozen times cheaper than traditional solar collectors, but we still need to increase the performance of our solar heaters and reduce their operating costs. This was my second step when I covered that black sleeve with cheap greenhouse film, and it increased the water heating temperature to more than 80 degrees Celsius. So, this is my third step, when I replaced the transparent film with glass, and this additionally increased the heating temperature, and now this thermometer measures the temperature of a small stream of the water from the heater, and we see that solar energy heated the water to 93 degrees Celsius when the ambient temperature was 25 degrees. However, it is only the middle of my road to cheap solar heat, and now I show my preparation for the fourth step when that polymer sleeve is covered with a thin steel sheet, and I hope that it will radically reduce the operating costs of our heaters. In addition, we can coat the steel sheet with selective coating, rather than usual black paint, and it will increase the efficiency of our heaters and the heating temperature of their water. Now I am showing my preparations for the fifth step, and this is an experiment with this additional mirror which significantly increases production of the heat and its temperature, but it is obvious that the additional mirror walls should be cheap, similar to these parabolic mirrors of my solar station. So, I will describe this solar heater, and this is my measurement of its energy parameters, and we can compare it with those old heaters with transparent film and without it, and this is the parameters of traditional solar collectors. This column describes how much heat is produced by 1 square meter of my heater during a sunny day, and this is different tasks for our heater in southern Germany for a hot summer day, and this column describes the heat production of 1 square meter of a traditional solar collector, which is about 10 times more expensive than our solar heater. This is an example of my calculation of the heat production of our heater during a sunny day, and this is the angle of incidence of sunlight to our glass, and not to the surface of that black film. Of course, this is only a prototype which was made for a variety of research, and we need large solar heaters which are even more than this my heater with an area of almost 5 square meters, and the large heaters are needed for solar stations which produce a lot of very cheap heat. In addition, our solar heater is interesting for solar stations of hot water supply or heat for industrial processes if these stations should be located on a horizontal roof, because traditional solar collectors require damage to the roof for their reliable fixation against a strong wind, while our heater is placed on the roof surface without that fixation and those damages, and it resists wind due to the horizontal orientation and large weight of the glass and the water inside the black film. This is the cost of materials for large heater with an area of almost 8 square meters, and we can see that this is less than $10 per square meter. This table describes the annual heat production from 1 square meter of our heater and the cost of our heat for different temperatures in the United States, Europe, and India, and I calculated the cost of the heat on the basis of this cost of capital and labor. These are the cases when the cost of our solar heat is approximately equal to the cost of heat from natural gas, and we see that they correspond to water temperatures of 65 or 85 degrees Celsius. However, a decrease in the temperature of the heated water significantly increases the annual production of our heat, and this reduces its cost, and these are the cases when our solar heat is about 10 times cheaper than heat from natural gas. This is an example of my calculation of the cost of the heat, and we see that I took into account the cost of construction, replacements of our black films, other operating costs and losses due to hail, because we will face the same problem as glass greenhouses which can be destroyed by a large hail. Obviously, we must choose the optimal glass thickness, and perhaps the optimal thickness will be about 4 mm, although we can decrease the thickness to 2 mm to reduce the cost of the heater, but this will increase the probability of destruction of the glass by hail. And we know that traditional solar collectors use tempered glass which can withstand large hail. In addition, we need to choose the optimal width of the glass to reduce losses due to hail, and the chosen width should correspond to some standard width of cheap polymer sleeves and some standard width of cheap glass sheets to avoid cutting the glass sheets because the cutting can increase our construction costs. This is my very approximate forecast of our losses due to hail, and experts on glass greenhouses can give us a more accurate forecast, and they can recommend methods to reduce the losses due to hail. In addition, we know that hail can usually happen only within a short season, lasting for 2 or 3 months, and for example, the American city of Phoenix can get caught in the hail only from mid-July to mid-October. Therefore, we can remove our glass sheets at the beginning of hail season, and after a few months the glass sheets are again installed, and we can see that these are easy operations because our glass lies on the black wooden walls without any fixation. The idea of temporary removal of our glass can make sense in countries with cheap labor, and one worker can remove or install several square meters of the glass sheets per minute. It is obvious that our heater will continue to operate in this condition during these several months, and my other videos describe the energy capabilities of such solar heaters and their maintenance. So, our solar heater is the same as this cheap heater, but we must add the glass and these black wooden walls, and we install those walls during the manufacture of these sections of expanded polystyrene and wooden battens. And I described this manufacture in my video which also showed the assembly of the solar heater, and we must assemble our heater in the same way, and then we put the glass sheets on those black walls. Now I show the gap between glass and wooden wall, and we see that the width of the gap can reach several millimeters, and it is obvious that such a large gap reduces the efficiency of the heater, but it provides a good ventilation of the space between the glass and the black film, and therefore moisture quickly leaves this space. Of course, we can use some kind of cheap sealing between our glass and wooden wall, and now I show one of the variants of the cheap sealing, but this variant requires testing. We know different methods of sealing the joint between adjacent glass sheets, and someday I will finish testing this idea of the sealing by means of narrow scotch. But now the joint of the glass sheets of my prototype has no sealing, and the sheets are joined without any gap. This is the situation after the rain, and we see that our joint of the glass sheets is almost impermeable to rainwater, but a small amount of the water passed through it and formed this puddle. And this is the situation in a few hours, and this is the impact of the puddle, but it is obvious that the puddle will gradually evaporate, and the moisture will leave the heater through those wide gaps under the glass. Certainly, sometimes we have to wash the upper surface of our glass, and those my heat cost calculations think that the average efficiency of our heaters is 70%, but it will be less if we refuse to wash our glass. In addition, these air bubbles reduce the efficiency of the heaters too, and therefore we must sometimes remove them. And we see that removing the bubbles is an easy operation if the glass sheets do not prevent us from doing it. Now I show that we have the ability to raise one edge of our glass sheets to remove the bubbles. In addition, the raised glass sheets allow us to remove dirt from the surface of the black film, and this dirt can be under the joints of adjacent sheets due to these puddles, but I am not sure that the operation of removing the dirt will make economic sense, because the lifespan of the black film will not exceed several years, and now I am showing the film which needs to be replaced in a few weeks or months because we see the appearance of small holes in the film, and soon their size will increase so that the normal operation of the solar heater becomes impossible. It is obvious that the lifespan of the black film depends on the brand of its polymer, temperatures of the heated water and the solar insolation in the region where the heater is located. But I hope that our glass will slightly increase the lifespan due to its absorption of ultraviolet radiation of the sun. This is my reminder that replacing the black film is a very easy and quick operation. The other features of our heaters are the same as for this case if our water temperature is less than 60 or 70 degrees Celsius, and I have described these features in my other videos, including schemes of connection of the heaters to pumps, but perhaps this type of water outlet will be more interesting for us, and I will describe it in my future videos. Now the water temperature is about 80 degrees Celsius, and we see the appearance of a large number of these bubbles which reduce the efficiency of the heater. That is why we should use industrial water which was made through deaeration if our goal is heat with a temperature of more than 60 or 70 degrees Celsius. Now I show one of my black films which has been heated by the sun to a temperature greater than 90 degrees Celsius several dozen times, and we see that the surface of the film has ceased to be smooth, and perhaps this phenomenon also slightly reduces the efficiency of the heater. In addition, this black film covered this surface completely a few months ago, when the film was new, and we see that now its length has decreased noticeably. Moreover, the high temperature dramatically reduced the lifetime of the film, and I remind you that this is the cheapest black film at a cost of 15 cents per square meter, and this is recycled low-density polyethylene, and its thickness is about 100 microns, but more expensive polymer films have a higher temperature resistance and a longer lifespan. I took into account those features here. And this is an example of calculating the cost of the heat with high temperature, and we see that I increased the cost of the solar heater, the cost of replacing the black film, and I increased the operating costs because we will more often do those operations of replacement of the film and removal of air bubbles.